Hello, welcome everyone to our Samsara AI and Data Speaker Series. I hope you're enjoying our AI-generated soundtrack we're kicking off with. So we're really excited to get started today. We have an excellent speaker. We have Professor Jorge Ortiz here to join us and talk about his research in sensing systems, interaction, multimodal learning within heterogeneous, densely sensed environments. He's currently at Rutgers University, where he leads the Cyber Physical Intelligence Lab within the Department of Electrical and Computer Engineering. And his lab aims to enable sense-making through novel sensing applications that enhance interpretation and understanding of complex multi-source data. So they're using state-of-the-art machine learning for a wide variety of real-world applications, including instrumented and smart environments, advanced driver assistance systems, collaborative robotics, and even smart healthcare. So some of his work in connection with this is related to the recently awarded $26 million NSF Engineering Research Center, the Center for Smart Streetscapes, where Jorge is also the principal investigator. And then just briefly, prior to his role at Rutgers, he was a member of the research staff at IBM Research, focused on machine learning and IoT systems. And he earned his master's and PhD from UC Berkeley in computer science following his undergrad in CS at MIT. So overall, very exciting speaker, very relevant to Samsara's work. And we're super excited to have you here today, Jorge. And with that, I'll turn it over to you.
Great. Thanks for the introduction. Let me go ahead and I guess I can share my screen now. Okay, very good. Everyone can see this, I assume. Very good. Okay, so again, thanks for the introduction. My work it's application driven in large part. We lead by working on interesting novel applications that bring together lots of different sensing modalities. So basically make sense of the world and explore what new kinds of applications and services we can provide on top of a substrate of deeply sensed environments. So I'm going to walk you through a few of maybe some of the higher level, more fundamental questions that we try to tackle in the lab, and then give you some, go through a few case studies where I walk you through some of the applications and things that we've built, both on the machine learning side and on the system side. And feel free to, I'll be looking at the chat wherever I can, whenever I can. But for now, I'm going to close it. So if anything pops up or whatever, and I actually don't know how that interaction is going to go, but perhaps we'll just wait for the Q&A session at the end, or let it queue up. I think we'll let the questions queue up.
That's right. There is a Q&A tab at the bottom of your Zoom screen, so people can use that. But we'll save most of the Q&A for the end. People can go ahead and ask their questions anytime, though.
Okay, very good, very good. Yeah, so that'll queue up, and then we'll take a look. All right, wonderful. So I just want to start by thanking the students who have been in my lab. Some of them are there now. We actually have a paper deadline tomorrow, so it's a bit of crunch time for us as well. But I'm, it goes without saying that without their hard work with my collaborators at various places and my current batch of students, that we wouldn't be able to sort of explore this domain. And it's really their hard work and diligence that has enables us to sort of dive in and learn some things here. So I wanted to thank them right off the bat. Okay, so I came from the sensing world from more than 20 years ago, where the objective was really how would the world look if we were embedding sensors throughout our spaces. And the question back there was really around, where do we put these things and how do we connect them? Is there an underlying computational substrate? And we're certainly seeing from the market, not just at Samsara. I used to be, before I joined Rutgers, I was at IBM Research, and I worked a bunch on IoT. So we're seeing that IoT market has certainly grown. We're seeing embedded devices and smart spaces in our homes. We can control them through our applications. We're seeing them to control, smart buildings, smart infrastructure. People are putting IoT devices on their bodies to be proactive about managing their health. And every day we're seeing new IoT devices hit the market, right? With things you can plug into the wall, things you can attach, tags that you can attach to various physical items, and the entire sort of suite of vertical software to manage this new ubiquitous sensing and computation substrate that we're embedding into the physical world. And for a long time in the research community, that was really it, right? It was really about how small can we make it? How energy efficient can we make it? How do we provide multi-hop, continuous connectivity? And for the most part, we've really gotten there in many countries, right here in the United States especially, where we don't even know how many sensing devices are around us in our environment. I'm sitting in an office building that has 100, 150 or so sensors per floor. I sit in my car, there's sensors all over the car, right? And so and all of these things are connected to the internet. So that's certainly not a research question anymore. But what we have started to think about is, well, now that we have this ubiquitous sensing and computation substrate, what are some interesting applications? And with the emergence of deep learning, generative AI, and many of the latest machine learning techniques over the last 10 or 15 years, we're starting to really merge those two together to think about, well, how can we enable new classes of applications on top of this computational and ubiquitous sensing substrate that is now all around us, right? So in my lab, we term this a computational space. And this computational space is where learning, sensing, and interaction overlap with each other. And it's within this intersection of these three components that we care to examine new kinds of applications and enable new kinds of interaction and sensing. And so just to give a sense for what we mean by multimodal, multimodal is used all over the place. We see it a lot in the machine learning literature. When we're talking about a modality in terms of multimodality, what we're talking about is, the sensory analog for humans is having, we have five senses. When we're talking about this in the context of sensing, we're really thinking of very broadly about the physical device that is modulated by a physical signal. And when we speak about a modality specifically, we're tying that to the physical signal that we're measuring. When we think about heterogeneity, we're thinking about the different types of sensors that are embedded in the environment. The other aspect of modality that we consider is the fact that we can create new modalities from these fundamental modalities. So for instance, you may have vibration as your raw modality, but you may have number of footsteps as a derived sensor, if you will, that comes from the vibration sensor. And in some cases, when we're designing our multimodal algorithms, we have to consider which kind of modality and what level of heterogeneity can we combine in order to provide a service or to enable a new kind of interaction in an application. So we'll go into examples of how we do that specifically and how we reason about it as we're constructing our models to make sense of the world. So what are the fundamental challenges? Well, the fundamental challenges in multimodal learning is always that, fundamentally these sensors live in their own measurement space. And so whether we're talking about temperature or magnetometer or sound, there's certainly a measurement space with a range of values and all the rest of it that are embedded in this measurement space. Oftentimes in these computational spaces, we want to combine them with more high dimensional sensing modalities. So video, audio, images, those live in their own pixel space. And we want to sometimes combine that with language as well, right? So we're really thinking about this fundamental challenge that they all live within a different space. There has to be some way in which we can bring them together. And the way that we bring them together is by using deep learning techniques that embed them into a common semantic space. And the properties of the semantic space are that the information across all of these different spaces are close to each other in semantic space when they are related to the same concept. And that's really what allows us to reason about the phenomena that we're measuring. And so the properties of multimodality that we examine specifically across these applications are the notion of fusion. How do we align the data? At what point do we stitch together aggregates of the data into meaningful features? With regard to representation, what kinds of architectures give us good representations for the objective? With regards to once we do have a representation, how can we explain or interpret that output? And that's something that's of prime importance as these models get more and more complicated, to kind of unpack the underlying reasoning that the model is making, or the kinds of correlations that it's exploiting in order to provide a level of explainability or interpretability. And finally, interaction. So how can they enable new kinds of interactions? So what kinds of signals can these computational spaces in the context of these learning models can we use to make sense of how an interaction is going, or when an interaction should happen with a human? So in some cases, it could be that an agent is using this information to infer what's happening and how to interact. In other cases, it could be that the human is providing feedback and we need to incorporate that back into the model, right? So these are some of the open questions that this general space is looking at, for which we're examining through our applications. So some of the applications that we're looking at in the Cyber Physical Intelligence Lab, we're looking at vehicular agents. So we have we design algorithms both in simulation and in practice, where people are actively driving and the vehicular agent is interacting with the driver while they're driving. And we'll see an example of that specifically. We're starting to look at applications in the context of urban sensing, where we want to essentially provide a service to the citizens of a densely packed, densely sensed urban space. The kinds of services where lights are extended if we notice that there's a mobility impairment, or where we can provide waypoint finding for the blind, right? So we're considering, how do we make sense of the world? How do we make sense of the street when we're collecting all this information and it's rapidly coming in? How can we build big and small models that sort of distill the right information to enable these new classes of applications? More locally, we've designed our own sense point. A sense point is literally a physical space at which you place a sensor, right? Or at least a sensor board. And our sensor board has 10 different sensors on it, and it gives us 18 different sensing channels. And so we want to do sense making in a smart office. What's happening? What's important? How do I interact? What can I query about the history of the space? And how can I use that to enable new kinds of optimizations? And finally, I think the human-robot interaction is a really interesting one, because a lot of these pieces start to come together in terms of both sense-making, interruption, and full interaction, right? And so what we're going to walk you through, I'm going to walk you through the case study where we've applied some of our techniques to enable more natural human-robot interaction. And so the fundamental question that our lab sort of drives a lot of the research that happens in the lab is, how does multimodal learning enhance the capabilities of co-learning systems, right? So we already know that co-learning happens perhaps at an application level, where you're sitting there and you're on a website and it's asking you questions and you're going back and forth, or when you're shopping and you're clicking. How do we cast that into the physical world, right? How do we make sense of what's happening? What does the person want? How do I interact with them? And of course, these are very, very broad questions. So we narrow those questions down by studying specific applications and designing techniques for those specific applications. With enough of these points, we can start to connect the dots and say something meaningful about the principles to build these kinds of systems. And so specifically, I think the big challenges in these spaces are, fusion and real time for these urban sensing and vehicular agents, the interaction and interaction timing in the context of human-robot interaction, And in the smart office, really understanding how, if you're taking a bunch of sensors and putting them together, how is it that the model knows what's happening? Can it explain what's happening and what correlations it's exploiting in order to make the inference that it's making? Okay, so I'm going to start with a case study on social timing. And the question is really about, when is a good time to engage? A fairly simple question, right? That for a lot of humans, it's a hard question even for some humans of knowing when to interact. Just if you hang out with kids for long enough, you'll know that they often interrupt when they have no sense of the fact that you might be talking to someone else. But we certainly want to build that level of awareness into our models, right? Especially when it becomes dangerous and to interrupt. So the first major project related to interaction and to timing is engaging with an active driver in a vehicle. And so actually the image that you see here on the lower right is of an instrumented vehicle where we've added extra cameras both inside and outside of the vehicle to get information about the driver and what they're looking at. We've also added physiological sensors to the driver in order to collect all of that contextual information. Now, we have to deal with, in interacting with a driver, the fact that they have varying engagement levels. And so timely interaction is not only a hard problem, but also you better get it right because it can be dangerous. It can distract the driver while they're driving. And the scene changes over time. So their cognitive load is dynamic and it's constantly changing. So one of the things that I think implicitly these models end up learning is, when is it that the cognitive load is low enough and the situation is not critical such that we can interact? And so this requires a nuanced understanding of the need for safe engagement and brings up interesting questions about control transitions. So let's say we have a model. Do we trust that it will not interrupt at a bad time? Can we start making decisions once we have this model that we understand about when we should hand off, either going to automatic driver mode or to hand it off to the driver entirely? And there's a whole transition in cognitive load when you do the handoff from the agent to the person. Now, we're not studying that specific question. We're only looking at the interrupt question, but the interrupt question leads to a bunch of other interesting questions, right, about when to do it. But really, believe it or not, when we spoke to the participants in the study, the main thing that they didn't want, the main concern that the driver specifically had, is that it wouldn't be annoying to them. So we want to manage the driver's distraction.
Once they're under my control, the entire world will be subject to my whims. Go away, you paperclip! No one likes you!
Right. So most companies actually don't want to build these interactive agents that interrupt you, because they just get annoying and people end up turning off these systems. And really nobody wants that. And fundamentally, I think most of the motivation for a lot of the work was, let's start with the high order bit of making sure this thing isn't annoying. Okay, so to give a little background on the specific data set that we collected, it's called the Is Now a Good Time dataset, or the INAGT dataset. It's publicly available. We collected for 64 drivers over 2,700 moments, 50 minutes long. The table you see here on the right is all of the different sensing channels that we were collecting. And this let me show you a video of what that interaction looked like. So when we basically have an agent randomly interrupt, we prompted the driver to answer yes or no of whether this is a good time to interrupt them. And this is what it looked like.
Is now a good time?
Yes.
Right, so all the information leading up to that question is collected. There's some amount of temporal context and of a time window, a fixed time window of data that we're incorporating with the input to this model. And the point at which we ask the question, the yes or no answer, is really the label that we're regressing to. So this is the design of the network that we put together in order to perform well on this data set. And as you can see, it's a multi-channel network. This work was from a few years back, so we're not using transformers or anything, any of the new sort of neural architectural components here, but we are leveraging some pre-existing models like Inception V1 to extract meaningful features from the scene rather than having to build it from scratch. Some of these channels, for instance, channels 2 and 3, actually channels 2, 3, and 4 are all learned from the 2,000 or so samples that we collected. So you can see this is not like a massive amount of samples in terms of yes and no. It was also highly biased, and there's most of the time people would say give one answer over the other. I don't remember if it was yes or no. I think they say yes most of the time. And so there were challenges with dealing with this kind of imbalance in the data. So I would say that one of the fundamental properties is really how much do we have enough data to train the model from scratch, and where we don't, can we either input a distillate that's meaningful, or in other words, an aggregated modality like we see in channel 4. Channel 4, we used open pose to extract face, hand, and body pose, right? So this is a pre-trained network that's extracting a new kind of aggregate or distillate from the input data. Channel 1, we're grabbing the features from Inception, and this was a big foundation model for natural scenes. And channels 2 and 3 are trained, the 2,000 or so samples that we had, we used a series of convolutional layers in order to extract meaningful time series features. And that worked very well. And we had to do all the stuff that you're probably building in-house at Samsara, like resampling and aligning, but that naturally comes with the territory when you're collecting multimodal data. Now, at the end of it, we do some late binding, we concatenate all the features, and pass that into a series of dense layers for the actual classification task. But more importantly, I think it's always the examples to sort of drive home the point that this architecture worked. So let me show you a yes example.
Is now a good time?
Yes.
Followed by a no example.
Is now a good time?
No. Getting on the freeway.
So interestingly enough, the model is able to pick up that the driver is leaning forward, that they're entering a fast-moving highway, that they look like they're distracted, and this is all from the multimodal fusion network. We took the same network and we created a task on Amazon's Mechanical Turk, asking the labeler if they thought the scene was safe. Is now a safe time to interrupt the driver? And the main objective there is that if we know if it's a good time and a safe time, that's the time to interact. And if either of those are no, it's not a good time to interact. And so we got a good score from that. But again, I have an example. This is where our model thought it was not a safe time.
Is now a good time?
So the driver was so distracted, he didn't actually answer the question. His cognitive attention was focused on doing the merge. And here, I think, and there are many examples just like that one, but here's, I think, one of the more interesting.
Is now a good time?
Oh, yes, I'm just making a turn.
Right, so that, it's not necessarily the case that that PASNet is wrong. It's really it really opens up a whole set of questions about whether our multimodal framework is able to fully capture the context. And perhaps this is 7 in the morning and there's no one on the street, and her cognitive load is actually quite low. Or her perception and understanding of the scene is incorrect. Right, and perhaps she's overconfident in her ability to multitask, right? And so this, again, we have a limited view of context. Even with these many cameras, we have 3 cameras inside and 1 outside, it still leaves open this question of, well, what was really the context and what's really a good answer here? I think in general, we lean towards safety. So we would say, no, unless we're absolutely sure, we're not going to interrupt. But that brings up yet another question, right? If you're too conservative, do we never interrupt? And actually, we tackle this question in the paper. We adjust the loss function to be very conservative. And so without having to decipher the graph too much, basically, we can prevent any annoying or unsafe interruptions altogether by adjusting the weights in our loss function. And actually, it's still left plenty of opportunities for interrupting on a 50-minute drive. And just to drive home the point that multimodality brings a lot of value, when we tried the same model with using only the cameras, our F1 score was 0.57. So we thought we got an almost 30% improvement on the F1 score by incorporating these other modalities. Certainly the camera has most of the interesting context in it, but we get a significant improvement in context awareness by incorporating other modalities. And so we have a paper in UbiComp a few years ago on this topic, and we've expanded this study. We have several other workshop papers and other projects that are in the works. So, this particular framework we thought was a very useful framework of dividing into multiple channels and then using sensor fusion to bring those pieces together. My colleagues at Cornell are actually, some of them are working on these social robot feeding scenarios. And in discussions with them, it seemed like PASNet would be a good solution for one of the big problems that their patients were complaining about, which is, I only want to use this robot when I dine alone because it's socially awkward when this thing feeds me. It doesn't seem to understand when is a good time to give me the food. So we adapted the PASNet model to this situation. We collected 30 triadic sessions of 90 people eating. Triadic sessions are basically 3 people eating at once. We trained the model only to look at 2 co-diners to infer whether it should feed the 3rd co-diner. And the reason we did that is because, so the hypothesis that we set forth in this is people socially signal to each other, they make eye contact, their lips are moving, they gesticulate. If you were all in the room with me, you might be nodding. If you're looking at me, the folks who are maybe not looking at me and not socially signaling to me that they're hearing me and understanding me, the model will pick that up, right? And so at least that was the hypothesis that we had. And so rather than have, the various cameras, the fundamental structure of PASNet was reused in this context to try to find if there was any patterns. And so what we did is we adapted the PASNet architecture, which we call this the sonnet architecture. And in this architecture, we broke it up. We partitioned each of the branches into their own channel, where each channel was dedicated to a particular person and was actually taking in multiple sensor modalities that was observing a single person's reaction. And we added these interleaved connections between the layers in order to capture correlations across channels that we believe capture the cadence of social signaling. And in fact, our model is shown to perform better with these interleaved channeling structure as an addition to the multi-channel architecture. And so our model, there are some results here that are all discussed in the paper. We implemented this on a fairly large model and then actually got it to run on a much smaller footprint of a device. I would say that it outperformed all the existing models in this space. I mean, that's a nice win, but really the graphs that we cared about are the preference votes and the level of distraction. So these are surveys of the diners before, with and without our algorithm. So if you look at these two bar charts here on the right, you can see that the learned algorithm, which is ours, which is the sonnet architecture, the number of folks who preferred the learned one was the highest, because they said it was in the surveys where we asked them how they felt about interaction with the robot when they used our algorithm, they felt that it was the most natural. So the level of distraction was also the lowest. So that's basically essentially what those two bar charts indicate, is that there's a perceivable, not just empirical improvement in the performance of the model, but a perceivable improvement by the end user that the model was doing something significantly different from the state of the art. And it was creating this more natural form of interaction. Okay, and this was a paper presented not too long ago at the conference on robot learning. Okay, so I'm going to switch gears a little bit, since I know we're at 3:30, but I'm going to just talk about one more case study, which isn't related to social timing. It's more related to explainability and interpretability in the context of a smart office. So, I know that it feels a little bit of like whiplash to sort of switch to this new topic, but it'll be the last piece that we're going to go through, and then I'll take questions. Okay, so another question that emerged in my lab outside of just interaction is, well, how do we know that any of this is doing, anything that the model is doing is meaningful? And this question comes up a lot in mission critical applications specifically, although we've been studying it in the context of a smart office. There's another project that we're working on in smart health, where the doctors are constantly asking, well, how do we know, right? How do we know that your model is picking out something that we can say something meaningfully clinical about, right? And so the whole notion of having a model be transparent enough to interpret the output and to explain how the output is related to the input is a fundamental challenge I think you're seeing throughout the machine learning community, right? But it's no different here, right? So on one end, we have highly interpretable models like random forests and decision trees, where it's very clear, what the thresholds are that the model is converging to. But those models have trouble dealing in a multimodal context. They're just not rich enough and don't have the model capacity to capture, more complex correlations between the inputs. So naturally, the academic community has shifted to looking at these deep models, but the deep models lose all their interpretability in terms of what the heck is going on. So we're trying to bring that interpretability using generative techniques. And so this work is actually, there's been this research branch that has emerged called general purpose sensing. General purpose sensing is the notion of having a single sensor, a single board with many sensors on it, and to try to make sense of of as much of the phenomena or the human activity that's happening around that sensor. And so it sort of deviates from having a single sensor with high signal to noise ratio for a particular phenomena, and rather one sensor with many sensing modalities on it, trying to make sense of as many different kinds of activities as possible. Okay, so here's a demo of from this work from Carnegie Mellon from 7 years ago now, called Synthetic Sensors Toward General Purpose Sensing.
A single sensor board in a room can capture a wide variety of events. On the right, you can see our board's raw sensor streams. This faucet running is easily seen in both the acoustic channel and by our high-speed accelerometers. Here we can see data from 3 different motor-powered appliances: a garbage disposal, a blender, and a coffee grinder. Note how each results in distinct sensor signals.
Now, those distinct, this was, wonderful work. It inspired a lot of the approach that we took originally. But what we saw were while the design and the vision are certainly there, there were still a bunch of open questions in the research community about how to make this, transparent. We could see visually that it was triggering the modulation pattern across certain sensors, but not others. How consistent is that was the question. The other one is, how well does that generalize, right? So, it also introduces this notion of having multi-ordered sensors, right? And so I think really the challenges have to do with the generalization of these synthetic sensors, right? If I were to take that sensor and put it in a different space, fundamentally the modulation pattern that's being picked up by those sensors, right? The actual pattern that's being recorded is going to be different. And so we wanted to, we noticed that the techniques that were proposed by this work and some of the derivative work are brittle to the context, right? Because fundamentally we're limited by the physics, and therefore its generalization is limited across environments. So we designed a similar sensor we called Maestro, and the purpose was to do our own deployment to test how much richer we can make our multimodal models to provide better generalization, more robust representation across environments, and even scalability, where we can create a sort of, activity foundation model that we can fine tune as we move it from one location to the other, because we can't change the physical attributes of signal propagation through a physical space. So we may just need to do some adaptation. And we're seeing that that's true across all of machine learning. So we proposed this system called GEXI. It's called the Generative Explanatory Sensor System. And what you're seeing here is an encoder-decoder model that takes in sensor data and produces two outputs. The intermediate layer produces something called a activation map that maps to the activation pattern of the input sensor. And so that's the middle layer. The output layer is a movie of what the sensor believes it is observing. And so each of these by themselves provide interpretability. Interpretability means I can look at the output or I can look at the activation map and know immediately, what the model is doing. Okay, so if I see someone riding a bike, it must be detecting that someone's riding a bike. If I see someone is dribbling a basketball or sitting on a chair, our model would generate an imagined or a dreamed movie of someone sitting on a chair, so it becomes clear. And that was really the objective. The other property is that we'd like the activation map, the pattern observed in the activation map, to correlate very strongly with the output that we observe, because that would provide a level of explainability, saying, oh, I see when you turn the drill bit on, sparks fly or whatever. And so therefore the light sensor is always activated when the drill bit is on, or maybe the audio sensor is spikes. And we want that to be consistent, because if that's not consistent, then you lose trust for the model. So I won't get into too much detail since it's 3:40 here, and I do want to leave a little bit of time for questions. But we designed an architecture to deal with small data, specifically to deal with small data by the introduction of this new module called the PMB-MLP-FFC. It's basically a signal processing component that's embedded in the deep architecture of the encoder. And this helps deal with the variations in the data, extracting some of the fundamental frequencies. We're not explicitly doing a fast Fourier transform. We're learning the kinds of transform we need to run on the input data. And there are some pre-processing techniques that we do to normalize and standardize the data and align it before it gets passed into the encoder. We also borrowed a technique known as these activation maps. This here is an activation map. An activation map is a heat map on an input, in this case an input image, that shows the pixels that the model weighed the most in its output classification. So the analog in the sensor domain is that we would show a heat map over the sensing modality that was triggering the movie we were generating. And so for instance, this is an example of an activation map. These are different activation maps extracted from different intermediate layers. The one that was most meaningful was at a particular layer in our architecture shown here on the left. The earlier layers, you can see over time, give a lot of weight to certain activations for different patterns, but over time, as it learns, you can see that the activation map has low variance and high identifiability with respect to the output. Okay, so fundamentally, the model is based on stable diffusion. We made updates to the stable diffusion model. Basically, we replaced that middle component with a fast Fourier convolution, and we use a 3D UNet in order to generate the movies. And so what we end up with is we start off with sensor space embeddings, and we end up producing imagined or dreamed movies. And there's similar work to this in the context of decoding people's thoughts. I think there was some work in Nature recently where they took signals from someone's brain and then showed images of what the person was thinking. And of course, this was pre-trained, right, with images of the thing. They asked them to look at some images and use those images as labels. We did the same thing. We trained by recording various activities with video and sensors, and then pass it into this modified diffusion network to generate movies from the sensor data. And we have a paper we've archived, but is currently being reviewed for publication, which is a similar concept. Okay, so this is I've been showing examples of the movies that we generate. This is a 4-frame GIF. It actually, we have our own lab server, one of these Lambda server boxes with 4 GPUs, and we have and believe it or not, that's a limited capacity when you're working with these these generative AI models. We're seeing that they actually are very computationally intensive. So we were only able to generate these 4 frame images, but GIFs, but we're actually moving those onto a HPC cluster with some high-end GPUs, and we expect that we'll be able to generate more elaborate movies. Probably we're probably never going to reach something like Sora, but I think we will see more interesting output coming from these sensor models. And we have a deployment now in my lab to collect more data. The interesting thing that we also stumbled upon is that you can generate movies of multiple activities, and they get cobbled together in interesting ways. And we're seeing that with the weirdness of the output of some of these diffusion movie generation models, but we see it as well in our data set. For instance, this is one single frame that's generating brushing teeth, typing, being in a meeting, and running all together in one frame. And it didn't quite blend them together, but it found a way to distribute them in pixel space. So we still don't know exactly, we still can't provide true transparency to how these GIFs are getting generated, but the generation of the movie is meaningful because we know what we collected. And in our experiments, we show that the model generalizes well. So if we take an external data set collected in a completely different environment and we look at the labels, we generate movies that match the labels. So very promising for relatively early work that we're looking to expand over the next few months. Okay, so I'll finish there. These are just some of the links to some of the papers that we've worked on, and I'll switch over to taking questions. Thank you.
Awesome. Thanks so much, Jorge. It's really fascinating work, and it's really relevant to our business also. We're working to apply a lot of this kind of research on multimodal machine learning to our customers. It's really exciting to see the evolution of this research. It's been close to my heart for years, and it's just really great to see the application of the latest AI techniques to this space. It's so valuable. Well, I think that's all we have time for today. And thank you again, Jorge, so much. This was just a great presentation. We're really grateful for your time. Thank you so much.
Yeah, it was wonderful being here. I wish I could have answered all the questions. All right. Thank you very much. Have a good afternoon, everyone. Bye-bye.